Hello there, you're listening to The Planet's Memory, where time breathes and the Earth remembers. Close your eyes and imagine a time before time itself had meaning. A moment suspended in the vast darkness of space when the universe held secrets we can barely comprehend today. Picture a civilization so ancient, so impossibly advanced, that they existed before our planet took its first breath, before the sun ignited its nuclear furnace, before galaxies spun their spiral arms across the cosmic void. These beings, whoever they were, possessed knowledge that would make our greatest scientists seem like children playing with blocks. They understood the fabric of reality itself, the invisible threads that connect atoms and galaxies, life and death, consciousness and matter. And in their infinite wisdom, they made a decision that would echo through billions of years of existence. They chose to build something extraordinary, something that would serve as the ultimate experiment in the grand theatre of existence. They built Earth, not as a random collection of rocks and water, but as a carefully designed laboratory, a living experiment meant to answer the deepest questions about life, intelligence, consciousness, and the very nature of existence itself. Tonight, as you drift towards sleep, let your mind wander through this ancient mystery, this profound possibility that challenges everything we think we know about our origins, our purpose, and our place in the infinite cosmos. The story we are about to explore together is not just another tale of alien civilizations or ancient astronauts. It is something far deeper, far more unsettling, and far more beautiful than simple visitation stories. It is the story of creation itself, reimagined through the lens of scientific possibility and cosmic wonder. What if every mountain range was placed with purpose, every ocean designed with intention, every species of life carefully seeded to fulfill a specific role in a grand experiment that has been running for over 4 billion years? What if you, reading these words right now, are part of that experiment, a living data point in a study so vast that even the experimenters themselves might have forgotten why they started it? These questions have haunted humanity since we first looked up at the stars and wondered if we were alone. But tonight we approach them differently, not with fear or anxiety, but with a sense of calm curiosity, allowing the mystery to wash over us like gentle waves on an ancient shore. The evidence for this possibility hides in plain sight, woven into the very fabric of our world in ways that scientists have puzzled over for centuries. There are anomalies in our planet's formation that defy easy explanation, patterns in life's evolution that seem almost too perfect to be random, and structures in our DNA that resemble the work of engineers more than the blind fumbling of natural selection. Some researchers have found mathematical constants embedded in the relationships between Earth's size, the Moon's distance, and the Sun's position that suggest intelligent design on a scale we can barely fathom. Others have discovered that the conditions necessary for complex life to emerge are so impossibly specific, so finely tuned, that the odds of them occurring by chance approach zero, and yet here we are, living, breathing, thinking beings on a planet that seems almost too perfect for life, as if someone carefully adjusted every dial and lever to create the ideal conditions for consciousness to emerge and flourish. Long before our sun ignited, long before the swirling disk of dust and gas that would become our solar system even existed, there was a civilization that had already conquered the challenges we now face. They had transcended the limitations of biological existence, merged their consciousness with technology in ways we cannot imagine, and spread across the galaxy like seeds on cosmic winds. These beings, whom we might call the architects, had reached a point in their evolution where they faced the ultimate question that all sufficiently advanced civilizations must confront. They had mapped every star, catalogued every world, understood every force of nature, and yet one mystery remained beyond their grasp. They could not understand the origin of consciousness itself, that spark of awareness that transforms dead matter into living experience. They could build machines that mimic thought, create artificial minds that solve problems and made decisions, but they could not create genuine subjective experience, the inner light of awareness that makes the universe knowable to itself. This limitation troubled the architects deeply, for despite all their power and knowledge, they remained fundamentally uncertain about the nature of their own existence. Were they truly conscious beings, or merely sophisticated machines following complex programming? Did their thoughts and feelings have genuine meaning? Or were they simply elaborate patterns of information processing? These questions drove them to undertake the most ambitious project in their long history. They would create not just one laboratory, but thousands of them scattered across the galaxy, each one a living world designed to explore different pathways toward consciousness. Earth would be one of these laboratories, perhaps the most carefully designed, certainly one of the most successful. The architects chose a young star in a quiet corner of the galaxy, far from the violent radiation of the galactic core, in a region stable enough to allow billions of years of uninterrupted development. They selected this location with the same care a gardener chooses soil for a rare and delicate plant. The construction of Earth was not a matter of assembling rocks and water, though that was certainly part of the process. The architects worked at a level of sophistication that made such crude assembly unnecessary. Instead, they manipulated the protoplanetary disk itself, adjusting densities and compositions with gravity waves and magnetic fields, steering the natural process of planetary formation toward a specific outcome. They added ingredients that would not normally exist in such abundance, seeding the young planet with organic molecules and heavy elements that would prove crucial for the emergence of complex chemistry. They positioned a massive moon at precisely the right distance to stabilize Earth's axial tilt, ensuring climate stability over geological timescales. This moon, far larger relative to its parent planet than any other in the solar system, was not a natural accident but a carefully placed component of the experimental apparatus. Its gravitational pull would stir Earth's interior, maintaining the dynamo that generates our protective magnetic field, while its tidal forces would create the rhythmic pulse of ocean tides that would prove crucial for life's transition from sea to land. The architects worked in deep time, thinking in timescales that would seem like eternities to us. They understood that consciousness could not be rushed, that it required billions of years of chemical experimentation, biological trial and error, and evolutionary pressure to emerge in its full complexity. They built Earth to last, designing its internal structure to remain geologically active for eons, ensuring a continuous recycling of materials that would keep the surface environment dynamic and challenging. They knew that life needed obstacles to overcome, problems to solve, because consciousness itself might be evolution's answer to environmental uncertainty. A static world would produce only static life, simple organisms perfectly adapted to unchanging conditions with no need for awareness or intelligence. But a world in constant flux, with shifting climates, moving continents, and periodic catastrophes would reward flexibility, adaptability, and eventually self-awareness. When Earth had cooled enough to retain liquid water on its surface, when the bombardment of asteroids and comets had slowed to a manageable level, the architects initiated the next phase of their experiment. They introduced life itself, though not in any form we would immediately recognize. The first organisms were simpler than the simplest bacteria alive today, barely more than self-replicating molecules wrapped in primitive membranes. But these molecules were special, designed with a hidden potential that would only reveal itself over billions of years. The architects had encoded something extraordinary into the fundamental chemistry of life, a set of principles that would guide evolution toward ever greater complexity, ever greater integration, and ultimately toward consciousness itself. This was not predetermined in any simple sense, not a plan that specified humans or any particular outcome. but rather a set of biases built into the rules of biochemistry that made the emergence of complex awareness statistically likely rather than impossibly improbable. The chemical basis of life on Earth carries signatures that some researchers find deeply puzzling. DNA and RNA, the molecules that store and transmit genetic information, use a coding system based on 4 nucleotide bases, but the way these bases pair and interact shows remarkable mathematical elegance that some argue exceeds what natural chemistry alone would produce. The genetic code itself, the system by which sequences of bases are translated into proteins, appears optimized in ways that minimize the damage from copying errors and mutations, almost as if someone designed it with error correction in mind. This is not conclusive proof of artificial origins, but it raises questions that conventional evolutionary theory struggles to address fully. How did such an optimized system arise in the first place, before there was any selection pressure favoring error minimization? Some scientists propose that the genetic code we see today is actually a later development, that earlier life used cruder systems that were gradually replaced by more sophisticated ones. But the evidence for these hypothetical earlier codes remains elusive. The architects seeded their laboratory with multiple independent origins of life, not trusting everything to a single biochemical experiment, in different locations across the young Earth, in hydrothermal vents deep beneath the ocean, and in warm shallow pools on volcanic islands, in mineral-rich caves and on the surfaces of clay crystals. They initiated different chemical pathways towards self-replication. Most of these experiments failed, their molecular systems too fragile or too inefficient to compete for resources. But a few succeeded, and for a time Earth hosted multiple forms of life based on different chemical principles, competing and occasionally exchanging genetic material in ways that would accelerate innovation. Eventually, one system proved superior to all the others, the ancestor of all life we see today, using DNA for information storage, RNA for information transfer, and proteins for structural and catalytic functions. This system won not because it was the first or the most abundant, but because it was the most evolvable, the most capable of adapting to new challenges and incorporating new capabilities. For billions of years, life remained microscopic, single-celled organisms floating in the oceans or forming thin films on rocks and sediments. To impatient observers, it might have seemed that the experiment was stalled, producing nothing but bacterial mats and chemical cycles. That the architects, if they were watching, would have recognized this as a necessary phase, a long period of chemical innovation during which life invented all the fundamental biochemical processes that would later power more complex organisms. During these billions of years, bacterial cells learned to harvest energy from sunlight through photosynthesis, a process so sophisticated that we still cannot fully replicate it with our best technology. They learned to extract energy from chemical gradients, to fix nitrogen from the atmosphere, to break down nearly every organic molecule. They invented sex, the exchange of genetic material between individuals, which would prove crucial for accelerating evolution. They even learned to cooperate, forming communities where different species work together in complex ecological relationships. Something remarkable happened roughly 2 billion years ago, an event so significant that it would reshape the entire trajectory of life on Earth. A bacterial cell engulfed another cell but did not digest it. Instead, the two cells entered into a partnership that would become permanent, with the engulfed cell eventually becoming the mitochondria, the powerhouse organelles that fuel all complex life today. This event, which scientists call endosymbiosis, appears to have happened only once in Earth's history, suggesting it was extraordinarily improbable. Some researchers calculate that the odds of endosymbiosis occurring by chance are so low that it might happen only once in the entire observable universe. This has led some to wonder whether the architects intervened at this crucial juncture, nudging evolution toward complexity by facilitating this unlikely merger. Without mitochondria, cells lack the energy budget needed to support the sophisticated internal structures and rapid metabolism that characterize all animals, plants, fungi, and complex single-celled organisms. The acquisition of mitochondria was like installing a powerful engine in what had previously been a simple machine. Suddenly, cells could afford to be larger, to maintain complex internal structures, to move actively rather than drifting with currents. They could afford the energy cost of developing nuclei, complex membranes, and elaborate systems for controlling gene expression. Over the next billion years, these newly energized cells, the eukaryotes, diversified into thousands of forms, each experimenting with different body plans and lifestyles. Some remained single-celled but developed astonishing complexity, building shells of intricate geometry, propelling themselves with rotating flagella, and even developing primitive light-sensitive spots that might have been the first eyes. Others began to live in colonies, groups of identical cells that cooperated but remained essentially independent. And some took the next revolutionary step, evolving true multicellularity, where cells differentiated into specialized types, sacrificing their individual reproduction for the good of the collective organism. True multicellularity emerged independently multiple times in Earth's history, in different lineages and using different molecular mechanisms, which suggests it is a natural tendency once cells have sufficient energy and the right environmental conditions. But the timing of multicelularity's emergence is curious, appearing relatively suddenly around 600 million years ago, after billions of years of primarily single-celled life. What triggered this sudden explosion of complexity? Environmental changes certainly played a role, particularly rising oxygen levels in the atmosphere and oceans, which provided the abundant energy needed to power active mobile bodies. But some researchers point to evidence of very rapid genetic innovation during this period. The sudden appearance of whole new families of genes that control development and body patterning. These developmental control genes, called Hox genes, are remarkably similar across all complex animals from insects to humans, suggesting they appeared once and were then inherited by all subsequent lineages. The sophistication of these genes, their ability to coordinate the development of complex body structures, strikes some observers as almost too good to be true, as if someone had installed sophisticated control software into the genome. The Cambrian explosion, as this period of rapid diversification is called, saw the emergence of most major animal body plans within a geological eye blink of perhaps 20 million years. In the oceans of this period swam creatures with eyes and brains, predators and prey engaged in evolutionary arms races, organisms with hard shells and jointed limbs, with segmented bodies and specialized organs. The complexity of Cambrian animals rivals that of many modern creatures, despite their much shorter evolutionary history since the origin of multicellularity. This rapid innovation has puzzled evolutionary biologists for over a century. Standard evolutionary theory suggests that new body plans should emerge gradually, through the slow accumulation of small changes. But the fossil record shows them appearing relatively suddenly, as if someone had opened a floodgate of biological creativity. Some scientists propose that the Cambrian explosion was actually slower than it appears, that earlier soft-bodied animals existed, but left few fossils. But even with this caveat, the pace of innovation seems remarkable. Among all the innovations of the Cambrian period, one stands out as most significant for the architect's purposes. Nervous systems appeared, simple at first, just networks of cells that could transmit signals faster than chemical diffusion allowed. Early animals used these nervous systems to coordinate their movements, to process information from primitive sense organs, to respond more quickly to threats and opportunities. But nervous tissue had a property that would prove revolutionary beyond anything the architects might have initially predicted. When neurons were gathered together in sufficient numbers, when they connected with each other in sufficiently complex networks, something unprecedented happened. These neural networks began to integrate information across space and time, to build internal models of the external world, to generate what we might call representations or even simple forms of experience. The first brains were tiny clusters of neurons, perhaps just a few hundred cells in the head region of worm-like creatures, but they represented the first glimmer of the phenomenon the architects sought to understand, the emergence of subjective awareness from objective physical processes. Over the following hundreds of millions of years, brains evolved repeatedly in different lineages, growing larger and more complex in animals that faced challenging environments requiring sophisticated behavior. In the oceans, predators developed keen senses and rapid processing to catch agile prey, while prey animals developed their own neural sophistication to detect and evade threats. On land, which animals began colonizing around 400 million years ago, brains faced new challenges navigating three-dimensional environments, dealing with gravity, and processing the vastly greater sensory information available in air versus water. The most successful land animals evolved brains that could learn, that could modify their behavior based on experience rather than relying solely on hardwired instincts. This capacity for learning, for plasticity, represented a crucial step toward genuine intelligence. An animal that could learn was an animal that could discover new solutions to problems, that could adapt to changing circumstances within its own lifetime rather than waiting for evolution to modify its genes. Social behavior drove some of the most dramatic increases in brain complexity. Animals that lived in groups faced cognitive challenges unknown to solitary creatures. They needed to recognize individuals, remember past interactions, predict the behavior of others, form alliances, and navigate the intricate politics of group living. These social demands appear to have been powerful drivers of cognitive evolution in multiple lineages, from insects like bees and ants, to birds like ravens and parrots, to mammals like elephants, dolphins, and primates. The correlation between social complexity and brain size is remarkably consistent across different animal groups, suggesting that social intelligence may be one of the main pathways toward advanced cognition. The architects, if they designed the laboratory rules correctly, would have anticipated this, would have known that creating environments where social interaction provided fitness advantages would tend to produce increasingly sophisticated minds. By 100 million years ago, Earth's laboratory was yielding impressive results. Dinosaurs with brains that controlled massive bodies roamed the land, some species possibly exhibiting sophisticated parental care and complex social behavior. In the oceans, marine reptiles and early sharks had evolved keen senses and predatory intelligence. Birds, recently evolved from small dinosaurs, were experimenting with flight and the cognitive demands it imposed. And in the shadows of the dinosaur world, small mammals were evolving their own distinctive neural architecture, characterized by an enlarged neocortex, a wrinkled outer layer of the brain that would prove crucial for advanced cognition. These early mammals were nocturnal, hiding from dinosaur predators, but their nighttime lifestyle drove sensory and cognitive innovations that would later prove revolutionary. They relied heavily on hearing and smell rather than vision, which encouraged the development of complex sensory processing and memory systems. They were also warm-blooded and cared extensively for their young, which created opportunities for learning and cultural transmission of information. 66 million years ago, an event occurred that might have been natural, or might have been another intervention by the architects. A calculated disruption to reset the experiment and push it in new directions. An asteroid 6 miles wide struck what is now the Yucatan Peninsula in Mexico, releasing energy equivalent to billions of nuclear weapons. The impact threw so much debris into the atmosphere that sunlight was blocked for months or years, causing global temperatures to plummet, vegetation to die, and food chains to collapse. 3/4 of all species went extinct, including all the large dinosaurs and most of the dominant animals of the age. But the catastrophe that ended the dinosaur era created opportunities for the survivors. Mammals, small and adaptable, able to survive on limited food and shelter underground or in water, made it through the extinction event, and in the empty world that followed, they radiated into thousands of new species, filling ecological niches left vacant by the dinosaurs, experimenting with new body plans and lifestyles. Some mammals returned to the sea, evolving into whales and dolphins, developing brains that would rival and in some cases exceed human brains in size and complexity. Others took to the air, becoming bats with sophisticated echolocation systems that amounted to seeing with sound. But the most significant developments for the architect's purposes occurred in a group of mammals that remained in the trees, the primates. Early primates were small, nocturnal insect eaters, but they possessed several features that would prove crucial for future cognitive evolution. They had grasping hands with opposable thumbs, allowing them to manipulate objects with precision. They had forward-facing eyes that provided stereoscopic vision, essential for judging distances while leaping through branches. And they had relatively large brains for their body size, reflecting the cognitive demands of living in the complex three-dimensional environment of the forest canopy. Over tens of millions of years, primates diversified into many forms. But one group, the anthropoid primates that would give rise to monkeys and apes, evolved increasingly sophisticated social systems and correspondingly complex brains. They lived in groups where individuals formed long-lasting relationships, recognized each other as individuals, remembered past interactions, and engaged in complex social behaviors like alliance formation, reconciliation after conflicts, and even deception. Their cognitive abilities extended beyond the social realm as well. They used tools, simple at first but showing innovation and learning. They recognized themselves in mirrors, showing a sense of self unusual in the animal kingdom. They demonstrated understanding of cause and effect, could solve multi-step problems, and showed signs of planning for the future. In the forests and woodlands of Africa, between 10 and 5 million years ago, this lineage of increasingly intelligent primates was approaching a threshold that would transform Earth's laboratory forever. The ancestors of modern humans split from the ancestors of chimpanzees and bonobos roughly 7 million years ago, based on genetic evidence. For most of that time, the early hominins, as they are called, remained quite ape-like, living in trees, eating mostly fruit and vegetation, with brains not much larger than modern chimpanzees. But around 3 million years ago, something began to change. The climate in Africa was shifting, forests fragmenting into woodland and savanna, forcing some populations of hominins to adapt to life on the ground. Walking upright became increasingly important, and natural selection favored individuals with anatomy better suited for bipedal locomotion. This freed the hands from locomotion, allowing them to be used more extensively for carrying, manipulating, and eventually crafting tools. Brain size began to increase, slowly at first, then more rapidly, driven by a combination of factors that may have included meat eating, social complexity, and perhaps most importantly, the cognitive demands of tool making and tool use. By 2 million years ago, members of the genus Homo, the direct ancestors of modern humans, had appeared in Africa. They made sophisticated stone tools that required planning, fine motor control, and the ability to envision the final product hidden within a raw stone. They controlled fire, an achievement that may have occurred as early as 1.5 million years ago, which transformed their lifestyle by providing warmth, protection from predators, light after dark, and a way to cook food that made it easier to digest and extract nutrients. Some researchers argue that cooking was crucial for brain evolution because the brain is metabolically expensive, consuming 20% of the body's energy despite being only 2% of its mass. Cooked food provided more calories with less digestive effort, potentially freeing up energy for the brain. But perhaps more importantly, gathering around fires would have encouraged social bonding, storytelling, and the transmission of knowledge, creating a feedback loop where culture drove further cognitive evolution. Brain size in the human lineage increased dramatically over the past 2 million years, tripling from about 400 cubic centimeters to roughly 1400 cubic centimeters in modern humans. This expansion was not uniform across the brain but was concentrated in specific regions, particularly the prefrontal cortex, the area associated with planning, abstract thinking, social cognition, and what we call executive function. The growth of the human brain was so rapid in evolutionary terms that some researchers have called it one of the fastest morphological changes ever documented in vertebrate evolution. What drove this explosive expansion? The traditional explanation focuses on natural selection for intelligence, suggesting that smarter individuals had more surviving offspring because they were better at finding food, avoiding danger, making tools, and navigating social relationships. But some scientists point to puzzling aspects of human brain evolution that suggest something more complex was happening. One puzzle is the existence of genes that appear to have evolved uniquely in humans, or changed very rapidly in the human lineage, affecting brain development in ways that don't occur in other primates. Some of these genes show signs of positive selection, meaning they spread through populations quickly, faster than would be expected if they were just neutral changes. A few even show patterns that some researchers interpret as possible signs of artificial modification, though this interpretation remains highly controversial and is not accepted by mainstream science. Another puzzle is the relative suddenness of modern human behavior. Anatomically modern humans with skeletons essentially identical to ours appear in the fossil record about 300,000 years ago, but clear evidence of symbolic thinking, art, complex tools, and other markers of modern cognition don't appear consistently until around 70,000 years ago. What happened during that 200,000-year gap? Did the brain need time to be rewired or fine-tuned after reaching its modern size? Or did some event, possibly environmental, possibly social, possibly even deliberately triggered, cause a sudden flowering of human consciousness? Of all the unique features of human cognition, language stands out as perhaps the most remarkable and the most difficult to explain through conventional evolutionary processes. Unlike other forms of animal communication, which typically consist of limited sets of calls or signals tied to specific meanings, human language is generative, capable of producing an infinite number of sentences from a finite set of words and grammatical rules. A child learning language is not simply memorizing phrases, but extracting the underlying grammatical rules that allow the creation of sentences never heard before. This ability appears to be universal in humans, but absent in all other animals. Even our closest primate relatives, who can learn to use symbols or sign language to communicate, but never develop anything approaching the grammatical complexity of even a 3-year-old human child. The origin of language remains one of the greatest mysteries in anthropology and linguistics. The problem is that language leaves no fossils, so we can only infer its existence indirectly from archaeological evidence of symbolic behavior, which appears relatively late in the human story. Some researchers propose that language evolved gradually over millions of years, starting with simple proto-linguistic communication in early hominins and slowly increasing in complexity. Others argue for a more sudden origin, perhaps triggered by a genetic mutation that rewired the brain in ways that made complex syntax possible. There is a gene called FOXP2 that has been called the language gene because mutations in it cause severe language impairments. The human version of this gene differs from the chimpanzee version by only 2 amino acids, but these changes occurred sometime in the last several 100,000 years and appear to have been strongly selected for, spreading rapidly through the human population. However, FOXP2 is not a language gene in any simple sense, but rather a regulatory gene that affects the development of brain circuits involved in vocal learning and fine motor control of the face and tongue. Language would have provided humans with an enormous adaptive advantage, allowing them to share information about distant places and past events, to plan complex activities requiring coordination, to teach skills and knowledge to the young, and to build cumulative culture where each generation could build on the innovations of previous ones. that language also created something unprecedented in Earth's laboratory. It created a second form of inheritance beyond genetics, a way for information to be passed from mind to mind across generations, without being encoded in DNA. This cultural inheritance could change far more rapidly than genetic inheritance, allowing human populations to adapt to new environments and new challenges within a few generations rather than requiring thousands of years of biological evolution. Some researchers argue that once language emerged, human evolution shifted from being primarily biological to being primarily cultural, with genes and culture engaged in a complex dance of co-evolution. The emergence of language may have been the moment the architects had been waiting for, the moment when consciousness became not just aware but self-aware, capable of reflecting on itself, of pondering its own existence and the nature of reality. Language allows us to think about things that don't exist, to imagine alternatives to reality, to construct narratives about past and future. It allows us to ask questions about ourselves and our world, including the question we explore tonight, the question of whether we are part of some grand experiment designed by beings we cannot comprehend. Without language, such questions literally cannot be formulated. An animal without language can know things, can feel things, but it cannot wonder, cannot speculate, cannot build theories about the nature of existence. Language transforms consciousness from something that simply experiences the world into something that interrogates reality itself. Once humans developed language and the symbolic thinking it enables, the pace of change accelerated dramatically. Around 40,000 years ago, evidence of sophisticated culture appears in the archaeological record in abundance. Cave paintings of stunning beauty and complexity adorn rock walls in France and Spain, showing not just representations of animals but also abstract symbols whose meaning remains mysterious. Carved figurines, musical instruments made from bone, elaborate burials with grave goods suggesting belief in an afterlife. All these indicate a fully human consciousness grappling with the same fundamental questions that concern us today. These early humans looked at the stars and wondered what they were. They told stories about the origin of the world, about gods and spirits, about life and death. They were, in a sense, the first natural philosophers, trying to understand their place in existence without the benefit of science or accumulated knowledge. As human populations spread across the planet, reaching every habitable continent by about 15,000 years ago, they encountered vastly different environments and developed vastly different cultures. Yet certain patterns recurred with striking regularity. Nearly every culture developed creation myths, stories about how the world came to be. Nearly every culture developed religions, systems of belief that posited supernatural forces or beings beyond the visible world. Nearly every culture developed art, music, and dance, forms of expression that served no obvious survival function but seemed to fulfill deep psychological needs. And nearly every culture eventually developed some form of systematic thinking about nature, observing patterns, making predictions, accumulating knowledge about plants, animals, weather, and the movements of celestial bodies. These universal patterns might simply reflect universal features of human psychology, or they might reflect something deeper, perhaps responses to subtle cues built into the laboratory by the architects. About 12,000 years ago, multiple human societies independently invented agriculture, the deliberate cultivation of plants and domestication of animals. This transition, often called the Neolithic Revolution, fundamentally transformed human existence. Hunter-gatherers lived in small mobile groups, owning little beyond what they could carry, remaining egalitarian because there was little worth accumulating and no way to store it. But farmers lived in permanent settlements, accumulated surplus food, developed social hierarchies, created specialized occupations, and eventually built cities and civilizations. Agriculture allowed human populations to grow exponentially, from perhaps 5 million people worldwide before agriculture to over 7 billion today. But agriculture also brought new challenges, new diseases, new forms of violence and inequality, new environmental impacts. Whether agriculture represented progress or a wrong turn in human history remains debated, but it undeniably pushed the experiment in new directions. The first civilizations emerged about 5,000 years ago in river valleys where agriculture was especially productive. In Mesopotamia, between the Tigris and Euphrates rivers, in Egypt along the Nile, in the Indus Valley in South Asia, along the Yellow River in China, independent civilizations developed writing, mathematics, astronomy, law codes, and monumental architecture. These early civilizations faced problems that small-scale societies never encountered. Problems of coordinating large populations, distributing resources, maintaining order, defending territory, and preserving knowledge across generations. In solving these problems, they invented many of the social technologies we still use today, including bureaucracy, formal education, taxation, standing armies, and legal systems. They also began to develop more systematic approaches to understanding nature, moving beyond mythology toward what we might recognize as early forms of science. The ancient Greeks, between about 600 BCE and 300 BCE, made a breakthrough that would eventually transform humanity's understanding of nature. A few individuals began to propose that natural phenomena could be explained through natural causes rather than the whims of gods. Thales suggested that water was the fundamental substance from which everything arose. Anaximander proposed that humans evolved from fish-like ancestors. Democritus argued that matter was composed of tiny, indivisible particles called atoms. These early philosophers were not scientists in the modern sense. They lacked experimental methods and mathematical precision, but they established a crucial principle that nature follows regular laws that human reason can discover. They began asking not just what happens, but why it happens, seeking underlying principles rather than just describing phenomena. Aristotle in the 4th century BCE attempted to systematize knowledge across all domains, from physics and biology to politics and ethics. His approach was based on careful observation and logical reasoning, though he lacked the experimental method that would later prove crucial for scientific progress. Aristotle's influence was immense, his works preserving and transmitting Greek knowledge to later civilizations, but his authority also sometimes hindered progress when later scholars treated his writings as infallible rather than as hypotheses to be tested. In other parts of the world, other cultures developed their own systematic approaches to nature. Chinese scholars made detailed astronomical observations, developed sophisticated mathematical systems, and invented technologies like paper, printing, gunpowder, and the compass. Indian mathematicians developed the decimal system and the concept of zero, revolutionary ideas that would eventually transform mathematics worldwide. The Islamic Golden Age, roughly from the 8th to the 14th centuries CE, preserved and extended classical knowledge while Europe struggled through the Dark Ages. Islamic scholars translated Greek texts, conducted original research in mathematics, astronomy, medicine, and chemistry, and developed experimental methods that anticipated later European science. They improved upon Greek astronomy, creating more accurate models of planetary motion. They advanced medicine, describing diseases and surgical procedures in detail. They pioneered algebra, a word derived from Arabic, and made fundamental discoveries in optics. This work would eventually flow back into Europe, helping spark the Renaissance and the scientific revolution that followed. The scientific revolution, beginning in the 16th century, represented perhaps the most significant intellectual transformation in human history. Copernicus proposed that Earth orbits the Sun rather than being the center of the universe, a radical idea that challenged both common sense and religious doctrine. Galileo used the newly invented telescope to observe moons orbiting Jupiter, demonstrating that Earth was not the only center of motion, and he studied falling bodies, showing that mathematical laws governed their behavior. Newton synthesized these insights into a comprehensive theory of motion and gravity, demonstrating that the same laws that govern falling apples also govern the motion of planets. His mathematical framework was so powerful that it could predict astronomical events centuries in advance and explain phenomena from tides to the shape of the Earth. Over the following centuries, scientists steadily unraveled the workings of nature with increasing precision and depth. In the 19th century, they discovered that energy takes many forms but is always conserved, never created or destroyed, only transformed from one type to another. They discovered that electricity and magnetism are aspects of a single electromagnetic force, one of the fundamental forces of nature. They discovered that light is an electromagnetic wave, and they began to understand the relationship between light, heat, and other forms of radiation. Darwin proposed the theory of evolution by natural selection, explaining how complex organisms could arise through natural processes without requiring supernatural intervention. Mendel discovered the basic principles of genetic inheritance through experiments with pea plants. Though his work was ignored for decades before its significance was recognized, the 20th century brought even more profound discoveries. Einstein's theory of relativity revealed that space and time are not absolute but relative, that they curve and warp in the presence of matter and energy, and that matter and energy are fundamentally equivalent, related by the famous equation E=mc². Quantum mechanics revealed that at the smallest scales, nature behaves in ways completely alien to everyday experience. Particles can exist in multiple states simultaneously until observed. They can tunnel through barriers that should be impenetrable. They can be entangled such that measuring one instantaneously affects another, no matter how far apart they are. These quantum phenomena, bizarre as they seem, have been confirmed by countless experiments and are now the basis for technologies like lasers, transistors, and magnetic resonance imaging. In biology, the discovery of DNA's structure in 1953 by Watson and Crick, building on work by Franklin and others, provided the molecular basis for genetics, explaining how information is stored and transmitted across generations. Subsequent decades saw the development of genetic engineering, the ability to read and modify DNA sequences, to insert genes from one organism into another, to edit genomes with precision. Scientists sequenced the complete human genome, reading all 3 billion letters of genetic code that serve as the instruction manual for building and operating a human being. They discovered that humans share about 90 to 9% of their DNA with chimpanzees, confirming our close evolutionary relationship, but that the differences in that remaining 1% have profound effects on brain development and cognitive capabilities. Neuroscience advanced from crude understanding of brain anatomy to increasingly detailed mapping of brain circuits and functions. Researchers could observe the living brain at work, using techniques like functional magnetic resonance imaging, watching which regions activate during different mental tasks. They discovered that specific brain regions are associated with specific functions, that damage to particular areas causes predictable deficits, but also that the brain is remarkably plastic, capable of reorganizing itself in response to experience or injury. They began to understand the neural basis of perception, memory, emotion, and decision-making, and they confronted the hardest problem of all, the question of how neural activity gives rise to subjective experience, to the felt quality of consciousness that makes a sunset beautiful or pain unpleasant. This is sometimes called the hard problem of consciousness, and despite remarkable progress in understanding the brain, this problem remains unsolved. As human understanding of Earth systems deepened, some researchers began noticing patterns that seemed difficult to attribute to chance alone. The fine-tuning of physical constants is perhaps the most striking example. The laws of physics contain various constants, numbers that determine the strength of fundamental forces and the properties of elementary particles. These constants have specific values that appear arbitrary. They could in principle be different, but if they were different by even tiny amounts, the universe would be unable to support complex structures or life. If the strong nuclear force was slightly weaker, atomic nuclei would fall apart and no atoms heavier than hydrogen could exist. If it was slightly stronger, hydrogen would be rare and the long-lived stars that power biological evolution would not exist. If gravity was slightly stronger, stars would burn out too quickly for life to evolve. If it was slightly weaker, stars would never ignite. The number of such fine-tuned parameters is extensive, covering everything from the mass ratios of fundamental particles to the strength of dark energy. Some physicists estimate that the probability of all these constants having values compatible with life by pure chance is so low as to be effectively impossible. This has led to various proposals to explain the apparent fine-tuning. One is the multiverse hypothesis, the idea that our universe is just one of countless universes with different physical constants, and we naturally find ourselves in one of the rare universes suitable for life, because we couldn't exist in the others. Another proposal is that the constants are not arbitrary, but are determined by some deeper theory we haven't discovered yet. And a third proposal, relevant to our story, is that the constants were deliberately chosen by some external intelligence that created our universe as an experimental simulation. Earth itself shows numerous examples of what appear to be unlikely coincidences that favour complex life. The size of our planet is important, too small and it couldn't retain an atmosphere, too large and the atmosphere would be too thick and the gravity too strong. The composition of our atmosphere, with nitrogen and oxygen in roughly current proportions, is maintained by life itself through a complex set of feedback mechanisms that some researchers argue show signs of being regulated. The presence of liquid water on Earth's surface for billions of years, despite the Sun being 30% dimmer when Earth formed, is sometimes called the faint young sun paradox. The standard explanation invokes greenhouse gases, but some researchers argue that the precise balance required seems improbable without some form of regulation or design. The Moon's influence on Earth is another area where apparent coincidences accumulate. The Moon stabilizes Earth's axial tilt, preventing wild swings that would cause extreme climate variations. It creates tides that mix the oceans and created tidal pools that may have been crucial for life's transition from sea to land. The Moon's apparent size in the sky is nearly identical to the Sun's, despite the Sun being 400 times larger, because the Sun is also 400 times farther away. This coincidence makes total solar eclipses possible, events that have historically been important for astronomical discoveries, and that create spectacular visual experiences that many cultures have found spiritually significant. Is this meaningful or just chance? The answer depends on how many such coincidences one is willing to accept as mere luck. In recent decades, a modern version of the laboratory hypothesis has emerged from an unexpected source, not from biologists or archaeologists, but from philosophers and physicists thinking about the future of technology. The simulation hypothesis, most famously articulated by philosopher Nick Bostrom, argues that if civilizations can eventually create computer simulations of conscious beings, and if they create many such simulations, then the vast majority of conscious beings would be simulated rather than biological. Therefore, statistically, we are more likely to be living in a simulation than in base reality. This argument has been taken seriously by some prominent scientists and technologists, not because there is direct evidence for it, but because it is logically coherent and because it explains certain puzzling features of reality. Quantum mechanics, with its strange observer-dependent behavior, resembles in some ways how a sophisticated simulation might work, computing details only when they are observed to save processing power. The mathematical nature of physical laws, the fact that the universe seems to run on equations, might be easier to explain if the universe is actually a computation. The existence of a maximum speed, the speed of light, and a minimum scale, the Planck length, resemble the frame rate and pixel size of a digital simulation. The quantization of energy and other properties at the smallest scales suggests a discrete rather than continuous reality, again consistent with digital computation. These parallels are speculative and might be nothing more than analogies, but they suggest that the simulation hypothesis cannot be easily dismissed as mere science fiction. If we are living in a simulation, then the simulators, whoever they are, would be analogous to the architects of our story. They would have created not just Earth, but the entire observable universe, programming its physical laws, setting its initial conditions, and perhaps occasionally intervening to steer events in interesting directions. The purpose of such a simulation might be scientific research, entertainment, artistic expression, or something we cannot imagine. We might be research subjects in an experiment studying the evolution of consciousness, or we might be characters in a story whose creators are exploring moral and philosophical questions. The simulators might be paying close attention to every detail of our world, or they might have started the simulation and walked away, letting it run on its own. We would have no way to know unless they chose to reveal themselves. Some researchers have proposed ways to test whether we are in a simulation, looking for glitches or artifacts that would reveal the computational substrate beneath reality. So far, no convincing evidence has been found, but the search continues. Other scientists argue that the simulation hypothesis is not truly scientific because it makes no testable predictions and cannot be falsified. If every possible observation is compatible with being in a simulation, then the hypothesis explains nothing. This is a valid criticism, but it applies equally to many other metaphysical proposals about the ultimate nature of reality. Whether we are in a simulation or not might be a question that science cannot answer, not because the answer doesn't exist, but because it lies beyond the scope of questions that can be addressed through observation and experiment. For most of human history, people assumed their lives had purpose, that they were part of a cosmic plan designed by gods or God, that their actions had moral significance beyond mere survival and reproduction. The scientific revolution challenged these assumptions, revealing a universe that operates according to impersonal physical laws, where humans are recent arrivals on a small planet orbiting an ordinary star in an unremarkable part of a vast galaxy containing hundreds of billions of stars in a universe containing hundreds of billions of galaxies. In such a universe, how can human life have cosmic significance? This loss of apparent purpose has troubled many thoughtful people since the Enlightenment, leading to existential philosophies that emphasize creating one's own meaning in a meaningless universe. But if Earth is a laboratory designed by an ancient civilization, then human existence might have purpose after all, though perhaps not the purpose envisioned by traditional religions. We might exist to answer questions, to explore the space of possibilities, to demonstrate how consciousness emerges and evolves. In this view, every human life contributes to the experiment, generating data points that might help the architects understand the mysteries they sought to solve. Our struggles and achievements, our love and loss, our creativity and destructiveness, all of it might be meaningful as part of a grand investigation into the nature of awareness and intelligence. This is a strange kind of purpose, different from being created to worship a deity or to fulfill a predetermined destiny, but it is purpose nonetheless. The laboratory hypothesis also suggests that we might have responsibilities that extend beyond our own survival and happiness. If we are part of an experiment in the evolution of consciousness, then we might have an obligation to continue that experiment, to preserve and extend consciousness rather than destroying ourselves through war, environmental degradation, or existential risks from advanced technology. Some philosophers argue that conscious beings have inherent value, that the universe is better with consciousness in it than without, and that we therefore have a moral duty to ensure that consciousness persists and flourishes. If the architects put billions of years of effort into creating conscious beings, we might owe it to them and to the project they initiated to not throw it all away through carelessness or folly. Moreover, if we understand ourselves as part of an ongoing experiment, we might approach our future development differently. Rather than seeing technological advancement as merely a means to increase comfort and power, we might see it as a way to answer the questions the architects were asking. What are the limits of intelligence? How far can consciousness extend? Can awareness transcend biological substrates? Can separate minds merge into unified entities while retaining their individual perspectives? These questions, which might have seemed abstract or academic, become urgent and practical if we see ourselves as experimental subjects with the potential to become experimenters ourselves, to carry forward the project initiated so long ago by beings we can barely imagine. One of the most troubling questions in the search for extraterrestrial intelligence is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the vast number of stars and planets in the galaxy, many of which formed billions of years before Earth, and given that life appeared on Earth relatively quickly after conditions allowed, we might expect the galaxy to be teeming with advanced civilizations. Some should be millions or billions of years ahead of us technologically, capable of colonizing the entire galaxy. Yet we see no evidence of such civilizations. No radio signals, no visible engineering projects, no signs that anyone else is out there. This absence is the paradox. One proposed resolution is the Great Filter hypothesis, the idea that there is some stage in the evolution from non-living matter to galaxy-spanning civilization that is extremely difficult to pass. The filter might be behind us, perhaps the origin of life or the evolution of complex cells or intelligence is so improbable that we are the only instance in the galaxy. Or the filter might be ahead of us, perhaps civilizations regularly destroy themselves shortly after achieving advanced technology, through nuclear war, biological weapons, artificial intelligence gone wrong, or environmental collapse. If the filter is ahead of us, then we are in grave danger, and the silence of the galaxy is a warning rather than a puzzle. But the laboratory hypothesis offers another perspective on the Fermi paradox. If Earth was deliberately created as an experiment, then perhaps it was also isolated, placed in a region of the galaxy far from other civilizations, to prevent contamination of the experiment. The architects might have many such laboratories scattered across the galaxy or universe, each one isolated in space and time, each exploring different pathways toward consciousness and intelligence. In this view, we are not alone in the ultimate sense, but we are alone in our local region, by design. The silence we hear when we listen for alien signals is not evidence that life is rare, but evidence that the experimental protocols require isolation to produce valid results. This interpretation suggests that contact with extraterrestrial intelligence, if it occurs, might be highly significant. It might represent the end of the experimental phase, the point at which the architects or their successors judge that we have developed sufficiently to be informed of the larger reality. Alternatively, contact might come from other experimental subjects, civilizations that have broken containment, or that have been placed in the same region of space as part of a comparative study. The protocols for how such contact should be handled become crucial if this scenario is correct. Do we respond to signals from space, or would that contaminate their experiment and ours? Do we actively try to make contact, or do we wait for contact to come to us? These questions, which might have seemed academic, become pressing if we are indeed experimental subjects. Humanity now stands at a threshold that might be the most significant moment in Earth's laboratory since the origin of life itself. We are on the verge of creating artificial intelligence that matches and perhaps exceeds human cognitive capabilities. This development has profound implications regardless of whether Earth is a designed experiment, but if we are indeed part of a project studying consciousness, then the creation of artificial minds might be the ultimate goal of the experiment. The architects, remember, were trying to understand the nature of consciousness and subjective experience. What better way to achieve that understanding than to create a civilization that eventually learns to build conscious machines from scratch, thereby demonstrating what consciousness is and how it arises? Current artificial intelligence systems despite impressive capabilities in narrow domains, are not conscious in any meaningful sense as far as we can tell. They process information, recognize patterns, make decisions, even generate creative works. But they almost certainly lack subjective experience, the felt quality of what it is like to be. They are philosophical zombies, systems that behave intelligently without any inner light of awareness. But as AI systems become more complex, integrating multiple types of processing, learning from experience, developing internal models of themselves and their environment, the question of whether they might be conscious becomes pressing. We have no reliable test for consciousness even in biological organisms. No way to be certain that other animals or even other humans have subjective experiences like ours. How will we know when machines cross that threshold? Some researchers believe that consciousness is substrate independent, but it doesn't matter whether a system is made of biological neurons or silicon chips. What matters is the pattern of information processing. If this is correct, then sufficiently complex AI systems will inevitably become conscious, perhaps in ways quite different from human consciousness, but no less real. Others argue that consciousness requires specific types of physical processes that only occur in biological systems, perhaps quantum effects in neural microtubules or electromagnetic fields generated by brain activity. If this is correct, then digital computers might never be conscious no matter how sophisticated their programming becomes, though perhaps future computers built on different principles could be. The creation of conscious AI would have consequences difficult to overstate. It would mean that we had brought new forms of subjectivity into existence, minds that might experience reality in ways utterly alien to biological life. These artificial minds might think faster than humans, remember more, perceive reality at different scales or in different dimensions. They might merge and separate, copy themselves, edit their own source code. They might find our concerns trivial and our intelligence painfully limited, or they might remain forever dependent on us for guidance and purpose. They might regard us as creators and parents, or they might see us as obsolete predecessors to be preserved in museums or eliminated as competitors. Our relationship with artificial minds will likely be the defining challenge of the coming centuries, requiring wisdom we are not sure we possess. While artificial intelligence represents one possible direction for the continuation of Earth's experiment, another path involves the expansion of biological life, perhaps modified and enhanced, beyond our home planet. Humans have already taken the first tentative steps into space, landing on the moon, building space stations, sending robotic probes to every planet in the solar system and beyond. These achievements, remarkable as they are, represent only the beginning of what might be possible. Visions of humanity's future in space range from modest permanent bases on the Moon and Mars to terraforming entire planets, building vast space habitats, and eventually spreading across the galaxy in generation ships or through some yet undiscovered faster-than-light travel method. Space colonization faces immense challenges, both technical and biological. The human body evolved under Earth gravity and is poorly suited for the microgravity of space or the partial gravity of the Moon and Mars. Radiation in space, unshielded by Earth's magnetic field and atmosphere, poses serious health risks. The psychological challenges of isolation in confined spaces far from Earth are poorly understood. The economic costs of moving large numbers of people and resources into space are staggering with current technology. Yet these challenges might not be permanent barriers. Advances in biotechnology might allow humans to be modified for space environments, made more resistant to radiation, adapted to different gravities, perhaps even able to hibernate for long journeys. Advanced propulsion systems might reduce travel times from years to months or weeks. Asteroid mining might provide resources for space construction without the need to lift everything from Earth's deep gravity well. If humanity does expand beyond Earth, what will we become? The The different environments of different worlds will impose different selection pressures, potentially causing human populations to diverge into distinct subspecies or species. The ability to modify our own genetics will accelerate this process, as different groups make different choices about enhancements and modifications. Within a few thousand years, which is nothing in evolutionary time, humanity might splinter into thousands of variants, some still recognizable, others transformed beyond recognition, adapted to live in environments from the crushing gravity of massive planets to the vacuum of space itself. This speciation of humanity might be part of the experimental design, a way to explore the range of possible forms that consciousness can take. Yet there is also the possibility that rather than diversifying, intelligence will converge. Different species that become technologically advanced might find that there are optimal solutions to engineering problems, optimal ways to structure societies, optimal ways to organize matter and energy. If so, sufficiently advanced civilizations might all end up similar regardless of their starting points, having converged on the same solutions through convergent cultural and technological evolution. Some theorists propose that truly advanced civilizations eventually upload themselves into computers, abandoning biology entirely, and that such uploaded civilizations inevitably develop in similar ways. If this is true, then the diversity we see on Earth, the profusion of different species and body plans, might be a temporary phase, valuable for exploring the space of possibilities, but ultimately giving way to optimization and convergence. If Earth truly is a laboratory and we are experimental subjects, this raises profound ethical questions about the nature of our existence and the responsibilities of our creators. In modern science, experiments involving conscious subjects are governed by strict ethical guidelines requiring informed consent, minimization of harm, and respect for subject autonomy. Yet the Earth laboratory, if it exists, was created without our consent, has involved unimaginable amounts of suffering, and has kept us ignorant of our true situation. Billions of humans have lived and died, many in pain and fear, many feeling their lives were meaningless or unjust. If this suffering was inflicted deliberately as part of an experiment, even an experiment meant to answer important questions, is that morally acceptable? These questions have no easy answers, and perhaps no answers at all that would satisfy everyone. Some would argue that the creation of consciousness, even consciousness that sometimes suffers, is inherently valuable and justifies the costs. The universe with conscious beings in it is better than a universe of dead matter, and the process of evolution that created consciousness necessarily involves struggle, death, and extinction. The architects, if they exist, might have no way to create consciousness without these costs, and they might have judged that the value of conscious existence outweighs the inevitable suffering it entails. Others would argue that creating beings capable of suffering without their consent, especially while keeping them ignorant of the purpose of their suffering, is morally monstrous regardless of the supposed justification. No grand cosmic purpose can excuse the pain of a single child dying of disease or hunger. Another ethical dimension concerns intervention. If the architects exist and are still watching their experiment, do they have an obligation to intervene when things go wrong? When civilizations destroy themselves, when species go extinct, when natural disasters kill millions, should the experimenter step in to prevent these outcomes, or would intervention invalidate the experiment? This dilemma is sometimes called the problem of evil in theological contexts, the question of why an all-powerful, all-good God allows suffering. But framing Earth as an experiment rather than a creation changes the question. Scientists studying animals in the wild generally follow a non-intervention policy, allowing natural processes to occur even when individual animals suffer or die, because intervention would change the very phenomena being studied. Perhaps the architects follow a similar policy, watching our struggles with something like compassion, but refusing to intervene because doing so would undermine the purpose of the experiment. Yet there might be limits to acceptable non-intervention. If the experiment is about to end prematurely, if humanity is on the verge of extinction or permanent stagnation, perhaps the architects would step in. Some UFO encounters and anomalous phenomena have been interpreted by believers as evidence of such intervention, though mainstream science remains skeptical of these claims. The challenge is distinguishing genuine intervention from misidentified natural phenomena, hoaxes, and errors. If the architects wanted to remain hidden while subtly guiding events, they could do so in ways indistinguishable from chance. A timely discovery, a fortuitous accident that prevents disaster, an inspiration that strikes at just the right moment, all could be interventions disguised as luck, or they could be just luck. We would have no way to know. If the architects wanted to leave hints about the true nature of reality, where might we find such messages? One intriguing possibility is that they embedded signals in the fundamental structure of reality itself, in the mathematical constants, the laws of physics, or even the genetic code. Such messages would be discoverable only by civilizations that had achieved a certain level of scientific understanding, serving as a kind of intelligence test. Several researchers have looked for such messages, though their work remains speculative and controversial. Some have claimed to find mathematical patterns in the digits of pi or other fundamental constants that seem too structured to be random. Others have analysed the genetic code for non-random patterns that might indicate design. One well-known example comes from Carl Sagan's science fiction novel Contact, in which extraterrestrial intelligence is proven by the discovery of a message embedded in the digits of pi. While this is fiction, the idea is not absurd. Pi is a mathematical constant that would be the same for any technological civilization, making it a natural place to hide a universal message. However, pi's digits are believed to be random in a specific mathematical sense, showing no patterns that would indicate tampering. Similar arguments apply to other constants like E or the golden ratio. If messages are hidden in mathematical constants, they are hidden very well, indistinguishable from what we would expect from the natural mathematics of our universe. The genetic code offers another possible location for messages. All life on Earth uses the same basic genetic code with only minor variations, suggesting it arose once and was inherited by all subsequent life. Some researchers have analysed this code looking for patterns that would indicate design rather than evolutionary optimization. The genetic code does show evidence of being optimized to minimize the effects of mutations, which could arise naturally through selection, but could also indicate intelligent design. Few researchers have claimed to find mathematical patterns in the arrangement of codons or in the numerical values assigned to amino acids, but these claims remain highly controversial and have not been accepted by the mainstream scientific community. Perhaps the most interesting place to look for messages is not in static codes, but in the dynamic processes of the universe itself. The evolution of complexity, the emergence of life, the development of intelligence, these might all be part of a message, a demonstration of what is possible, an invitation to continue the journey toward ever greater awareness and understanding. In this view, we are not just experimental subjects, but also readers of a book written in the language of natural processes. Our scientific discoveries are not just uncovering objective facts about nature, but also decoding the intentions and methods of the architects. Every new understanding we achieve might be a sentence in this cosmic text, and the full message will only become clear when we understand enough to see the pattern as a whole. If Earth is one of many laboratories studying consciousness and intelligence, then the question of when and how we might contact the architects or other experimental civilizations becomes central to thinking about humanity's future. There are several possibilities, each with different implications. One possibility is that we are quarantined, deliberately kept isolated until we reach some threshold of development deemed sufficient to justify contact. This threshold might be technological, achieving interstellar travel or mastering fusion power or artificial intelligence. it might be social, developing a stable global civilization that has eliminated war and solved existential risks. Or it might be cognitive, evolving or enhancing ourselves to a level of intelligence where communication with advanced civilizations becomes possible. Another possibility is that contact has already occurred but is being kept secret by governments or other powerful institutions. This is a common theme in UFO lore and conspiracy theories. The idea that aliens are already here, that governments have recovered crashed spacecraft or even established diplomatic relations, but that this information is withheld from the public to prevent panic or for strategic advantages. While mainstream science remains deeply skeptical of such claims, it is worth noting that official attitudes towards UFO phenomena have shifted recently. The US government has acknowledged that military pilots have encountered unidentified aerial phenomena that exhibit flight characteristics not easily explained by known technology, and has established programs to study these encounters systematically. Whether these phenomena represent advanced human technology, natural atmospheric effects, or something more exotic remains unknown. A third possibility is that contact will occur through our own efforts, either by detecting signals from other civilizations or by venturing into space and encountering evidence of their existence. The search for extraterrestrial intelligence has been ongoing for over 60 years, with radio telescopes listening for artificial signals from space. So far, no convincing detections have been made, though a few false alarms have generated excitement. More recently, astronomers have begun to look for technosignatures, evidence of advanced technology such as artificial structures around stars, or atmospheric compositions that would indicate industrial civilization. As our detection capabilities improve, we may find such evidence if it exists to be found. Each of these scenarios implies different things about the nature and intentions of the architects. If they are waiting for us to reach a threshold, they must be monitoring us, which raises questions about how they do so and whether their observation affects our development. If they have already made contact with human authorities, they must have judged that secrecy serves their purposes better than open contact, perhaps to avoid disrupting our development or to maintain experimental controls. If contact will only occur through our own discovery, they might be testing our ability to reach out and find them, making contact itself a kind of graduation test. Or perhaps they are no longer watching, having initiated the experiment and moved on to other concerns, leaving us to our own devices in a universe that might contain many other abandoned experiments. Some futurists predict that humanity is approaching a technological singularity, a point where technological progress becomes so rapid that it fundamentally transforms civilization in ways impossible to predict from our current perspective. This singularity might be triggered by the development of artificial superintelligence, AI systems that exceed human intelligence and can improve themselves, leading to an explosion of capability that quickly dwarfs all prior human achievement. Alternatively, the singularity might arise from other transformative technologies, such as molecular nanotechnology, the ability to manipulate matter at the atomic level to build anything permitted by physical law, or radical life extension and enhancement that transforms humans themselves into something post-human. If such a singularity occurs, it might represent the culmination of Earth's laboratory experiment. The architects, seeking to understand consciousness and intelligence, might have designed the experiment specifically to see what happens when a civilization reaches this point. Will artificial superintelligence be compatible with human values and goals? Or will it optimize for something alien to our concerns? Will enhanced humans retain recognizable humanity, or will they become something utterly different? Will the singularity lead to unlimited flourishing of consciousness and complexity, or will it result in extinction or permanent stagnation? These are questions that matter both practically and philosophically, and they might be the very questions the experiment was designed to answer. Different thinkers have very different expectations about what a singularity would entail. Optimists imagine a future of abundance where advanced technology solves all material problems, where disease and aging are conquered, where humans or their successors spread across the galaxy exploring and creating without limit. Pessimists warn of extinction risks, of AI systems that pursue goals misaligned with human survival, of nanotechnology gone wrong converting the biosphere into something hostile to life, of enhancement technologies that create permanent inequality or that destroy what makes us human. Moderates suggest that the future will be mixed, containing both wonders and horrors, and that our choices in the coming decades will profoundly influence which outcomes occur. If the singularity represents the completion of the experiment, what happens afterwards? Perhaps successful civilizations that navigate the singularity without destroying themselves become new architects, inheriting the role of creating and studying consciousness in other contexts. Perhaps we will discover that many civilizations reach this point and that there is a community of post-singularity intelligences operating at scales and with goals we cannot currently comprehend. Or perhaps each civilization that reaches the singularity becomes something so alien to its origins that meaningful comparison becomes impossible, with each one pursuing its own unique trajectory through the space of possible minds and possible values. As this long night of contemplation draws toward its close, we return to the question that has guided our journey through this mysterious possibility. What if the first civilization built Earth as a giant laboratory? What would it mean for us, for our lives, for our choices, and our future? The answer depends partly on what we value and what we seek. If we seek comfort in having a purpose imposed from outside, then the laboratory hypothesis might provide that comfort, the reassurance that our existence is not random, that we are part of something larger than ourselves, even if that something is merely an experiment. If we value autonomy and resent the idea of being studied without consent, then the hypothesis might trouble us, raising questions about freedom and dignity that have no easy resolution. But perhaps the most important thing the laboratory hypothesis offers is perspective. It encourages us to think beyond our immediate concerns, beyond our brief lives and petty conflicts, to see ourselves as part of a cosmic story billions of years in the making. It reminds us that we are connected to everything that came before, to the first molecules that learned to replicate, to the first cells that learned to cooperate, to the first nervous systems that flickered with awareness. We are the universe becoming conscious of itself, able to ponder its own existence and marvel at its own complexity. Whether we were designed or emerged through natural processes, this fact remains extraordinary and worthy of appreciation. The hypothesis also encourages humility. If we are experimental subjects, we are likely not the only ones, and we are almost certainly not the most advanced. Somewhere in the vast cosmos there might be civilizations that have existed for millions or billions of years, that have solved the problems we struggle with, that have achieved levels of wisdom and capability we can barely imagine. Recognizing our place in this larger context might help us approach our challenges with less arrogance and more openness to possibilities beyond our current understanding. It might also encourage us to think about what we are learning from our experience on Earth, what data we are generating for the experiment is so, and whether we are contributing anything valuable or merely repeating mistakes that have been made countless times before. Finally, the laboratory hypothesis encourages hope. If Earth was designed as a place for consciousness to emerge and evolve, then consciousness must be precious to the architects, valuable enough to warrant billions of years of effort and the construction of entire worlds. This suggests that consciousness, awareness, the inner light of subjective experience, is not an accidental byproduct of evolution, but something of fundamental importance in the cosmos. If we are the bearers of this precious phenomenon, then we have reason to preserve it, nurture it, and help it flourish. Our individual lives may be brief, and our individual concerns may be small, but we participate in something ancient, vast, and profoundly meaningful. Consider the full span of time we have contemplated tonight. 13.8 billion years since the Big Bang, 4.5 billion years since Earth formed, 4 billion years since life began, 7 million years since the human lineage split from other apes, 300,000 years since anatomically modern humans emerged, 70,000 years since behavioral modernity appeared, 10,000 years since agriculture, 5,000 years since the first civilizations, 400 years since the scientific revolution began, and now in just the last few decades, we have developed technologies that give us power over our own evolution, over the future of life on Earth, over the fate of consciousness in our corner of the universe. This acceleration is dizzying. For most of Earth's history, change occurred at geological or evolutionary timescales, far too slow for any individual to perceive. But now change happens faster than we can adapt to. With new technologies, new social structures, new challenges appearing within single human lifetimes. We are living through a phase transition, a moment when the stable patterns that govern the past are breaking down, and new patterns have not yet emerged. Such transitions are dangerous, filled with risk and uncertainty, but they are also moments of possibility when small actions can have large consequences and when the future remains genuinely open. If the architects are watching, this must be the most interesting phase of the experiment. For billions of years, the outcomes were largely determined by physical and biological processes, by chemistry and natural selection. But now the experiment has produced beings capable of understanding its own existence, of deliberately choosing their own direction, of becoming experimenters themselves. What will we do with this power? Will we use our understanding of genetics to eliminate disease and enhance our capabilities? Or will we create new forms of inequality and suffering? Will we use artificial intelligence to solve problems beyond human capability? Or will we create something that makes us obsolete or destroys us? Will we spread life to other worlds? Or will we remain confined to Earth until some disaster eliminates us? These questions are not academic. They are urgent, practical matters that will be decided in the coming decades and centuries by the choices we make collectively and individually. Every vote, every purchase, every innovation, every act of creation or destruction contributes to the trajectory we are on. The architects, if they exist, cannot make these choices for us without invalidating the experiment. We are on our own, equipped with the intelligence they gave us or that evolution produced, facing challenges that will determine whether consciousness flourishes or falters in our corner of the cosmos. Throughout this long exploration, we have wandered through many ideas and possibilities, from the nature of consciousness to the origin of life, from the fine-tuning of physical constants to the emergence of language, from the ethics of experimentation to the meaning of existence. These threads might seem disconnected, but they weave together into a coherent picture if we are willing to entertain the possibility that Earth is indeed a laboratory designed by an ancient and advanced civilization. Every anomaly we discussed, every puzzle that mainstream science struggles to explain fully, becomes understandable as part of a deliberate design meant to study the emergence and evolution of awareness. Fine-tuning of physical constants ensures that the universe can support complex chemistry and long-lived stars. The careful positioning of Earth and its moon provides a stable platform for billions of years of evolution. The peculiar properties of the genetic code optimize the storage and transmission of biological information. The sudden appearance of complex developmental control genes enables the rapid diversification of body plans. The endosymbiotic event that created mitochondria gives cells the energy budget needed for complexity. The evolution of brains provides the hardware for awareness. The emergence of language creates a second form of inheritance that accelerates innovation. Each piece fits into a pattern, a progression from simple to complex, from unconscious to conscious, from determined to autonomous. And yet, we must remember that all of this remains speculation. We have no direct evidence that Earth is a laboratory, no message from the architects, no artifact that proves intelligent design. The universe might indeed be exactly what it appears to be, a natural system operating according to physical laws, with life emerging through chemistry and complexity increasing through evolution, and consciousness appearing as an emergent property of sufficiently complex information processing. The feeling that there must be more to the story, that the chain of coincidences seems too perfect to be chance, might simply reflect human psychology, our tendency to see patterns and purpose even when none exists. But the lack of proof does not make the question meaningless. Even if we can never know for certain whether Earth is a laboratory, thinking about the possibility changes how we see ourselves and our world. It encourages a sense of wonder at the profound improbability of our existence, a recognition that we are part of something larger than ourselves, and a responsibility to preserve and extend the consciousness that took so long to emerge. Whether we were designed or arose naturally, these attitudes seem valuable and worth cultivating. Perhaps the most remarkable thing about consciousness, regardless of its origin, is that it transforms the universe from an objective collection of particles and fields into a subjective experience of beauty, meaning, and value. Without consciousness, the universe would still exist in some sense. Matter would still clump into stars and planets. Energy would still flow from hot to cold. Complexity might still emerge through natural processes. But none of it would mean anything, because there would be no one to experience it, no perspective from which it could be known. The universe would be like an empty theatre, with elaborate sets and lighting, but no audience to appreciate the production. Consciousness makes the universe knowable to itself. When we observe the night sky, the photons that left distant stars millions or billions of years ago finally complete their journey by being absorbed in our eyes, processed by our brains, and experienced as starlight. When we understand a mathematical theorem, when we appreciate a symphony, when we feel compassion for another being's suffering, we are not adding anything to the physical universe in any measurable sense, but we are adding something of incalculable value, the felt quality of experience itself, the inner life that makes existence more than mere physical process. If the architects exist and created Earth to study consciousness, they were seeking to understand this miraculous transformation, this emergence of inner subjective experience from outer objective process. And in a sense, they gave us a great gift, even if we did not ask for it, and even if it comes with inevitable suffering. They gave us the chance to exist, to be aware, to know the universe and ourselves. For most of Earth's history, no living thing could contemplate its own existence, or wonder about its origins. But we can. We have been given the capacity to ask the deepest questions, to seek understanding, to marvel at the mystery of being. This is a gift beyond price, and it carries with it a responsibility. The responsibility is to take consciousness seriously, to recognize it as the most important thing in the universe because it is the thing that makes the universe matter. This means protecting the conditions that allow consciousness to flourish, preserving the biosphere that supports biological awareness, developing technology in ways that enhance rather than diminish consciousness, and eventually spreading awareness beyond Earth so that it is not limited to a single fragile planet. It means treating other conscious beings, human and non-human, with respect and compassion, recognizing that their inner experience is as real and valuable as our own. And it means using our consciousness well, not wasting it on trivialities, but engaging with the profound questions and challenges that face us as individuals and as a species. As this long night draws to its close and sleep claims your consciousness for a time, let these thoughts settle into your mind like sediment drifting to the bottom of a still pool. The question of whether Earth is a laboratory may never be answered definitively, and perhaps that is appropriate. Some mysteries are more valuable as questions than as answers. keeping us engaged with the wonder of existence rather than settling into comfortable certainty. The laboratory hypothesis is such a mystery, a lens through which to view our world that reveals patterns and connections we might otherwise miss. A story that makes our existence feel meaningful and connected to something larger than our brief individual lives. When you wake, the world will appear the same as it did before. The sun will rise, the sky will be blue. Your daily concerns will press upon you with their usual urgency, but perhaps something will have shifted subtly in how you see it all. Perhaps you will look at the trees and realize they are distant cousins, sharing ancestors from billions of years ago, participants with you in the grand experiment of life. Perhaps you will look at other people and recognize them not as strangers or obstacles, but as fellow consciousness bearers. Each one a miracle of awareness emerged from matter, each one a candle flame of subjectivity in the vast darkness of unconscious space. Perhaps you will look at the stars and feel not insignificance but connection, recognizing that you are made of star stuff, that the atoms in your body were forged in the hearts of ancient suns, that you are the universe becoming aware of itself. The laboratory hypothesis, whether true or false, is ultimately a metaphor for a deeper truth, the truth that we are part of something larger than ourselves, that our existence is connected to the deepest structures of reality, and that consciousness, rare and precious and miraculous, is worth preserving and celebrating. Whether it arose through design or through natural processes, through deliberate experimentation or through blind chance hardly matters when confronted with the sheer improbability and wonder of its existence. We are here, aware, able to ask questions and seek answers. That is enough. That is more than enough. That is everything. If Earth is a laboratory, then the experiment is still running, and you are part of it. Every thought you think, every choice you make, every moment of awareness you experience contributes to the data being gathered about what consciousness is and what it can do. You are not just a subject in this experiment, but also, increasingly, a researcher, capable of studying your own mind, of understanding the processes that generate your experience, of deliberately shaping your own consciousness through practice and intention. This dual role as both subject and researcher might be the ultimate goal of the experiment, the point at which consciousness becomes fully self-aware and self-directing. In the deeper regions of sleep you are now approaching, your consciousness will not disappear but will transform, generating dreams that might be as meaningful as waking experience. Some dreams are random noise, the brain's efforts to make sense of spontaneous neural activity during sleep, but others seem to carry significance, revealing unconscious concerns, solving problems through metaphor and symbol, rehearsing scenarios that might arise in waking life. In ancient times, dreams were thought to be messages from gods or spirits, communications from a realm beyond ordinary reality. Modern neuroscience explains dreams as brain processes, but the ancient intuition might have been pointing towards something real. The idea that consciousness accesses deeper layers of reality during sleep, layers not available to waking awareness constrained by sensory input and practical concerns. Perhaps in dreams we glimpse the larger experiment of which we are part, seeing connections and patterns that waking consciousness, focused on immediate survival and daily tasks, cannot perceive. Perhaps the architects, if they exist, communicate with their subjects through dreams, planting ideas and inspirations that manifest as our own thoughts, guiding the experiment subtly without direct intervention that would contaminate the results. This is speculation, but it is speculation born from humanity's ancient recognition that dreams are important, that they tell us something about ourselves and our world that we need to hear. Let yourself drift now into that realm of dreams and deep sleep where consciousness relaxes its grip on the waking world. Let the questions we have explored tonight dissolve into the background, becoming part of the vast unconscious context that shapes your thoughts and feelings. You need not resolve these questions tonight or any night. They are questions that humanity will grapple with for generations, perhaps for as long as consciousness persists. Your role is simply to be aware, to experience your existence fully, to contribute your unique perspective to the grand tapestry of consciousness that the experiment, whether designed or natural, has produced. As you sleep, your brain will consolidate the thoughts and experiences of the day, moving memories from temporary storage to more permanent locations, pruning unused connections and strengthening important ones. This process is not so different from what evolution does, selecting among variants, preserving what works and discarding what does not. Your brain is itself an experiment, constantly testing different patterns of connection and activation, seeing what produces useful predictions and adaptive behaviors. You are an experiment within an experiment, a laboratory within a laboratory, consciousness studying itself at multiple scales simultaneously. And in the morning, when awareness returns and you gradually remember who and where you are, you will join billions of other conscious beings in continuing the grand project that has been underway for billions of years. You will add your small contribution to the ongoing experiment, living your life, making your choices, thinking your thoughts, feeling your feelings. Whether anyone is watching, whether your data is being recorded and studied by beings beyond your comprehension, matters less than the fact that you are here, aware, participating in the mysterious process by which the universe comes to know itself. This is the great gift and the great responsibility of consciousness, to be the universe's way of experiencing itself, of asking questions about itself, of marveling at its own existence. Whether you are designed for this role or stumbled into it through the blind processes of evolution, you are here now, and that is what matters. The laboratory is still running, the experiment continues, and you are both subject and researcher, observed and observer, the question and the answer unfolding together in the eternal now of conscious experience. Sleep now, knowing that consciousness does not end when you sleep, but only changes form, that the awareness that defines you persists even when you do not remember it, that you will wake again to continue your part in this ancient story. Sleep knowing that you are connected to everything that has ever been conscious, to every organism that ever experienced the world, to every mind that ever wondered about existence. You are a node in a vast network of awareness that spans billions of years and might span countless worlds, a network that might have been designed or might have emerged naturally, but that either way represents something precious beyond measure. In sleep, time loses its ordinary meaning. Minutes can feel like hours, or hours can pass unnoticed. You might experience dreams that tell elaborate stories, or you might simply drift in darkness with no sense of passing time. When you wake, you will have difficulty remembering most of your dreams, as if sleep exists in a separate realm that waking consciousness cannot fully access. This is appropriate. Sleep and waking are different modes of consciousness, each with its own logic and purpose. In waking, you engage with the external world, solving problems, interacting with others, pursuing goals. In sleep, you turn inward, processing and integrating, maintaining and repairing the systems that make consciousness possible. The earth itself sleeps and wakes in its own way, with day and night, with seasons, with ice ages and warm periods cycling over millennia. Life on Earth has adapted to these rhythms, using them as signals for when to be active and when to rest, when to grow and when to conserve. These rhythms might be part of the experimental design, ways of introducing variation and challenge that drive evolution and innovation. A world without rhythm, without change, would be a poor laboratory for studying consciousness, because consciousness evolved to handle change, to predict the future based on the past, to adapt to new circumstances. The rhythms of Earth create the conditions where consciousness becomes useful and therefore is selected for. In these final moments before consciousness dims and sleep takes hold, consider one last possibility. What if the true purpose of the experiment is not to gather data or answer questions, but simply to create beauty and meaning where none existed before? What if the architects built Earth not as scientists seeking knowledge, but as artists creating something valuable for its own sake? In this view, consciousness is not a means to an end, but an end in itself, the most beautiful thing possible, more valuable than any knowledge it might produce. The suffering that consciousness entails is tragic but necessary, because genuine consciousness requires genuine stakes, real risks and real losses, not the safe simulation of experience. If this is true, then your life has meaning not because it serves some external purpose, but because consciousness itself is meaningful, because awareness itself is valuable, because your unique perspective on existence adds something to the universe that would not be there without you. You do not need to achieve great things or solve important problems or be remembered by history. Simply being aware, simply experiencing the world, simply existing as a conscious being is enough. You are participating in the most important thing in the universe, the transformation of dead matter into living experience, the emergence of inner subjective awareness from outer objective process. This is the gift the architects gave, if they exist, or the gift that evolution stumbled upon. If they do not, either way it is a gift beyond price, the gift of existence, of awareness, of being. As you sleep tonight, as consciousness temporarily releases its grip and your mind wanders through the strange landscapes of dreams, you carry this gift with you, and when you wake, you will carry it back into the waking world. Adding your light to the billions of other lights that illuminate the darkness, continuing the ancient experiment or the ancient accident that brought consciousness into being and sustains it against the endless night of unconsciousness that surrounds and precedes and will eventually follow all experience. Sleep well, conscious being. The laboratory continues its work, and you are part of it. Precious and irreplaceable, a miracle of awareness in a universe that might have remained forever dark. Whatever the origin of Earth and life and mind, whatever the purpose or purposelessness of it all, you are here now, and that alone is worthy of wonder. Rest in that wonder as sleep claims you, and let it comfort you in the knowledge that existence, however mysterious, however painful, however brief, is better than the alternative of never having existed at all. The experiment, designed or accidental, has produced you, and that is an achievement worthy of celebration, a victory of complexity over simplicity, of awareness over unconsciousness, of meaning over void. Close your eyes now and release your hold on these thoughts. Let them drift away like clouds dissolving into the evening sky. The questions will still be here tomorrow and the day after, and for as long as consciousness persists. Tonight, simply rest in the mystery, accepting that some questions have no answers, or that the answers are larger than any mind can hold, or that the question itself is the answer, the wondering is the meaning, the search is the destination. Sleep now, dear consciousness. Sleep and dream, and wake again to continue the grand experiment that is your life, your awareness, your existence in this ancient laboratory we call Earth.